And we're back. Welcome back from the weekend and happy Tuesday. Today we're going to switch gears a little bit and talk about another type of Bayesian classifier, particularly Bayesian networks. And before we begin, let's take care of some administrative bits. The reading for this material, Introducing Bayesian Networks, is on the Blackboard in the supplementary material area. Generative classifiers. When we last met, we talked about generative classifiers as using or mimicking or modeling the probability that generates the label instance pairs, that is, the feature vectors along with their respective class labels. And if we can get that joint distribution that generates or mimic it or model it, we can use conditional probability, the sum rule and the product rule, and come up with an expression that we call Bayes' rule. And in particular, if we can form the posterior distribution of the class label, we can define that as the product of the data likelihood and the prior distribution over class labels divided by the normalization factor. And we said that all of these terms on the right-hand side of this expression for Bayes' rule, you can calculate quite readily from the data. The likelihood function describes what you've seen. And for this, in the context of a spam classifier, you collect all the spam, all the ham examples, and then you compute the probabilities of the variable instantiations for each of those groups. So you segregate your data by the class label. Likewise, the prior distribution, you describe the proportions of the target variable outcomes. You collect all the spam, all the ham, and you compute the proportions of your data set for the number of spam examples you have divided by the total size of the data set, and the number of ham examples you have divided by the total size of your data set. And then, of course, the posterior distribution, we use Bayes' rule to compute that. All right, so we also talked about random vectors, and we can compactly write the random vector for d many variables, x1 through xd, and this is the compact notation. We can expand that out into the joint distribution or the random vector for each one of these features in d dimensions. And so we said we can apply the product rule to this joint distribution where the two variables of interest are the first variable and the condition is on that vector of the remaining variables. Okay, so we do that again and again, recursively and again, and we end up with a factorization involving the product of smaller distributions, smaller meaning the query variable only has one variable. And so we can write an equivalent expression of this joint vector in d dimensions, joint probability distribution, as the product of a number of these smaller factors. So we'd say xd times d, xd minus 1 given xd, times this term, times this term, times this term, and so forth. And so there's more than one way of using the chain rule or forming the chain rule, and each one of those ways represents the multiplication of a different factorization of this joint probability distribution. So that brings up the idea of conditional independence. Conditional independence between two random variables, we say they're conditional independent variables x and y. If when you condition on a third variable, we'll call that z, and that could be a vector or a singular random variable, it could be a random vector or a random variable, is equal to the product of x given z times the product of y given z. And so what this says is that if you know z, you do not need x in order to predict information about y. So how would we depict this in a Venn diagram? Here we have our universe of consideration, our sample space omega, and we have two events, x and y, in our Venn diagram. So let's draw such a z, and if you condition on z, that means you change your universe of consideration from everything that's in the universe of consideration to this region we're calling z. And it just so happens if we condition on z, that x and y, the portions of x and y that are only inside that new area z, do not overlap. And so now this part of x and this part of y and let me shade that in, this part of X and this part of Y are independent from one another. They do not overlap in the Venn diagram. So this is what conditionally independent means. And when things are conditionally independent, if you can find the right condition, your joint probability distribution can get it to factor quite nicely, and it's a lot easier to solve for a large joint distribution because you're now solving it as the product of a bunch of independent parts. And so this conditional independent is a powerful mechanism that we'll use to form a generative classifier, so-called Bayesian network. So let's take a look at how we represent these factors in a Bayesian network. Now, of course, in modern age, there's a lot of smart devices and data in which we can traffic. There are things that are, by today's standards, fairly mundane. We have smart watches here that measure all sorts of things like oxygen saturation, pulse, EKG. We have our smartphones. We have smart bodysuits that measure certain biometric information. Smart meters, oh, that's very commonplace. There are shoes that have tracking devices and measure all sorts of things about pressure and forces on your feet. Smart infrastructure for things like roadway bridges for detecting things like corrosion and stress and strain to help with prediction. And this is an interesting application, a smart cane for visually impaired to detect individuals, detect obstacles, and things like that. And so there's a lot of data streaming around. And for all these different data types, some parts of the data depend on other parts of the data. So here's an example of a system that you can buy now that has many different quantities that you can measure. Your random vectors consist of variables that are measurements, each one of which is from a different quantity. But these measurements performed by these random variables in a vector, they're related to one another. And so if we can use those relationships and encode those relationships, we can make our life easier in trying to factor a large joint distribution in order to make the Bayesian classification much simpler. And so here is the MySignals kit from Libelium, and it has an Arduino-based computational platform here, and you plug into it a lot of different sensors. One sensor is for pulse oximetry, so that's pulse and oxygen saturation. We have EKG here for your heart signal. We have a core temperature measurement. Here's a glucose measurement. Here is, let's see if we can find the core temperature. A galvanic skin response. This is the core temperature. And then the galvanic skin response measures the moisture on your skin, how sweaty you are. And here is a blood pressure cuff. And so you have all sorts of measurements that you can have or take with this kit. And some of them are pulse, oxygen saturation, ECG, core temperature, respiration. And certainly you don't have to just take the measurement itself. If it's a temporal streaming data measurement, like oxygen saturation over time, you can certainly compute derivatives over these raw measurements. And so if you have X representing your O2 saturation, d dt of X, O2, is how that oxygen saturation changes over time. And then we can also compute the second derivative of this oxygen saturation to look at the curvature in the signal over time. And so we have lots of sensor measurements that we can make. Now we can model these dependencies. In particular, the example I gave is the derivative of a signal versus the signal itself. We can model this using probabilities. And we can now, if we model these dependencies using probabilities, you can capture the joint probabilities as a graphical structure to assist in managing the dependencies between nodes to help you in choosing the notional right factorization leading to this joint probability distribution. So that's at the heart of what Bayesian networks do. Bayesian networks, as we'll see later, are just finding a good factorization where we're encoding conditional independence between nodes. And so let's define a graph. It's a double consisting of two sets, V the set of vertices, and E, the set of edges. So let's have each random variable, and there are n of them, x, x1 through xn, and these are going to be the vertices in our graph. And then we have edges that are directed edges, so they have a direction, and these are drawn from the subset of V cross V. And so these edges are going to encode a direct dependency of one variable on another. So for example, if we had a random variable measuring the pulse, and we had the derivative of that pulse, well, that random variable for the pulse is going to influence this derivative. Said differently, we say this derivative of the pulse, the rate of change of your pulse, is going to depend on the pulse. And that sort of makes sense graphically, but now we can depict it to very easily and right away see the relationships between these two variables, the derivative of pulse, rate of change, and the pulse itself. And so each random variable is a vertex, and each directed edge encodes a direct dependency. And so here we have a graph fragment, and the strength of the relationship between two different variables is going to be quantified by this conditional probability, these conditional probability distributions. They're associated with each node. And so when we construct all of these dependencies, we're going to get a graph. Specifically, we're going to get a directed acyclic graph. So there are no loops, no cycles in the graph. And this has an abbreviated name called a DAG. DAG is a directed acyclic graph. And so what happens is you buy this system, and a knowledge engineer, someone comes in, and they encode all the dependencies associated between variables, be they direct variables from sensors or variables that are computed from information from the sensors, and builds this Bayesian network. And so in doing so, you determine what these causal dependencies are, and in doing so, you construct the directed acyclic graph, the DAG, in order to depict all of the conditional dependencies between variable pairs among your measured quantities from the sensors. And so here, we talked about the chain rule, and we said how you peel off the query variable from the condition variables will give rise to a different factorization of this original d-dimensional joint probability vector. And so this particular factorization, we had each one of these variables going from left to right as your query, and then the remaining were the condition, and then we had a joint distribution here involving the remaining variables. And then we further applied the product rule and factored off again. And when we're done, we bottom out with probability xd, and then all of these factors, xd, xd minus 1 given xd, xd minus 2 given xd minus 1, xd, and so forth, going all the way up. All of these factors along this left-hand edge, those are going to be the factors you multiply together in order to comprise the equivalent expression for this original joint distribution. And so a conditional probability term, probability of xd minus 1 given xd, means that xd minus 1 is not independent of xd. It's causally dependent. So knowing something about xd will tell you something about xd minus 1. So if we look at the second to last factor in our graph, we have the probability of xd minus 1 given xd. And so what that means is that xd minus 1 is not independent of xd. It's causally dependent. Knowing something about xd tells you something about xd minus 1. And so how we'd model this is we'd say xd, how we'd model this, is we would have our node for variable xd, that is the condition, and we draw an edge inbound, directed edge, to xd minus 1. And so that means that xd minus 1 is causally dependent on xd. Knowing something about xd, our condition variable, tells you information about xd minus 1. And so we're going to draw such a graph fragment. We're going to draw such a graph fragment for every single factor that involves a condition. So we'd model it thusly. We'd say xd causes or influences xd minus 1. And so the vertices in the DAGs with no inbound edges, they're independent. Here we have xd involved in a marginal probability, and because it has no inbound edge in the graph fragment, it means that it is independent. It does not depend or is not influenced by another node. And so here, if we're going to represent this probability of xd minus 1 given xd times probability of xd, we'd have our node for xd. There's no inbound edge. It's not conditioned on anything. And we draw an inbound edge to xd minus 1. And so vertices in the DAG with no inbound edges are independent, whereas vertices in the DAG with inbound edges are so-called causally dependent on one another. So that means xd minus 1 is causally dependent on xd. Okay, so let's take a look at how these variables might take form. Now, certainly when you build a Bayesian network, you have to look at the nodes and their possible values. And these values have to be mutually exclusive, collectively exhaustive, and they're assumed to be discrete. But not all variables are discrete and not all variables are finite. And so you can have different types of values. You can have Boolean values for variables taking on true or false. You can have categorical values for your variables that cover multiple states. For example, pollution could be low, medium, or high for some definition of low, medium, and high. An integer could capture all that is possible. So let's say if you had an age variable, age can go from 1 to 120 or 130, for example, enough to cover all the ages that you might encounter for a measurement. If you have a real value quantity, you can cover all of the possible values by quantizing those real values. So for example, if you have temperature, you could say freezing temperature is minus 40 degrees Fahrenheit to 32 degrees. Cold is over 32 degrees to 50 degrees. And warm, you could say, is over 50 degrees up through 80 degrees. And so if you're dealing with real value quantities and you want to build a Bayesian network, you have to quantize your values to be discrete. And so now, if you're going to choose values for your variables, you're going to choose those that are as descriptive as possible of the domain that you're trying to model in order to satisfy this task. And you do it as efficiently as possible. So you don't want your quantization to be too fine-grained, but you want it to be fine-grained enough to describe the phenomena of interest. So for example, if you're dealing with patient records and maybe you're dealing with patient ages, you might quantize it in terms of baby, child, adolescent, young, middle-aged, or older. If you're dealing with a daycare, well, daycares deal with children, so you're going to quantize it on a more fine-grained scale. Maybe it's newborn, infant, crawler, waddler, someone who's new to walking but not yet walking, toddler, pre-K, pre-kindergarten, and kindergarten, right? So in both of these cases, for patient ages, it ranges among the different categories, but for daycare ages, as a variable measurement, you're going to be very fine-grained with the different age groups within the child category. And so in the example that we have in the reading, we have a number of variables. One's called pollution, smoker, cancer, dyspnea, and X-ray. And they're going to be of type binary for pollution, Boolean for smoker, cancer is a Boolean, dyspnea is Boolean, and X-ray is binary, positive or negative. And so we have low, high for pollution, true, false for smoker, cancer, and dyspnea. And by the way, dyspnea means shortness of breath. And X-ray, its binary values are going to be categorical. They're going to be positive or negative. And so we have two categorical variables, pollution and X-ray, and we have three Boolean variables, smoker, cancer, and dyspnea. Okay, so let's take a look at the network structure. So this is a Bayesian network that some knowledge engineer has gone in and proposed. We have as our independent nodes, we have pollution and smoker, and these are going to influence the cancer node. And so we draw the inbound edges, leaving pollution and smoker, that are directed edges incident to the cancer node. And then likewise, we have cancer has outbound edges, and they're incident to X-ray and dyspnea, respectively. Now, this is the Bayesian network for the lung cancer problem. And we populate based on the counts that we have in our example data set that you might call from patient records. We populate a bunch of probability tables. Now, certainly if you are independent, you have a single probability table, but if you're causally dependent, you have a joint probability table. And so here, cancer, it's conditioned on pollution and smoker, so we have all of the values of our conditions for our binary variables for pollution and smoker. And then we fill in the respective probabilities. In this case, we only list the probability table for the possibility where cancer equals true. To get the same cancer equals false, we just use log total probability, subtract each of these values from 1. Okay. And so here is our Bayesian network. And in Bayesian network literature, they often use family metaphors to describe the nodes. And so you have each of these nodes as a random variable, and we talk about the parents of a node are those nodes on the inbound side, on the non-arrow side of an incident edge in the directed acyclic graph. And so the cancer variable, it has 2 parents. Those are pollution and smoker. So we talk about parent, we also talk about child. The cancer node, a child node, is on the non-arrow side of an edge, of a directed edge. So cancer node has 2 children. They're going to be the X-ray variable and the dyspnea variable. And then we also talk about siblings. Here, siblings are at the same level in the graph. Siblings share the same parent. So here, X-ray and dyspnea, they are siblings in this Bayesian network, in this directed acyclic graph. And then we also talk about ancestors and descendants. So dyspnea has as its ancestors cancer and pollution has as its descendants cancer and dysnopia. Okay, and so we use also tree terminology when we're describing a Bayesian network. We talk about the root node being at the top, that's a graphism from computer science. We also talk about a leaf node as those nodes that don't have any children, and they're typically drawn at the bottom of the graph. So we always arrange these trees, these graphs, so that the arcs are from top to bottom direction. And so here, pollution and smoker are the root nodes. We traverse these directed edges in a bottom direction until we get to the leaf nodes, which are always at the bottom. And the leaf nodes, by definition, from graph theory, are those nodes that do not have any children. And so there's another concept that's really important called the Markov blanket. And the Markov blanket provides statistical isolation. And this Markov blanket can be calculated from the graph, from this visual Bayesian network, by taking a node, looking at its parents, and its children, and its children's parents. And it just so happens, if you condition a node on all of the other nodes in its Markov blanket, it will be independent from all the other nodes in the graph. So suppose we have the following graph fragment. So let's say we have a node here, a node here, and let's say we have some child nodes here. And let's just populate this with a bunch of other nodes here. And let's see, let's come down here, Let's come down here. Let's not come down there. So let's come here and let's come there. So here's a node X. And if we take X and we take its parents, okay, so its parents are here. Its parents are here, here. Its children are here and here. And its children's parents, so the parents of its children are here and here. Now, if we have other nodes in this graph, let me just draw some other nodes. And if we condition node X on its Markov blanket, so here's the Markov blanket. I'm going to call this the Markov blanket of node X. And so if we write the probability of X and condition on the Markov blanket of X, that's going to be independent of all the other nodes in the graph. And so what that means is the probability, and let's call this X, let's call this V1, V2, V3, V4, and we have X. And so if we want the probability of V1, V2, V3, V4, X, conditioned on the Markov blanket of X, well, that just makes X independent from all the other nodes. That's the same as the probability of V1, V2, V3, V4, given Markov blanket of X, times probability of X given Markov blanket of X. And so this idea of conditional independence that we said before allows you to factor this joint distribution into the product of simpler distributions because of this conditional independence. And so the Markov blanket, which is the node's parents, children, and the children's parents, if we condition a node on the Markov blanket, it becomes independent from all the other nodes in the graph. So that's a really important property for being able to factorize a large joint distribution into the product of simpler distributions. And it makes it a lot easier to solve for things like Bayes' rule. Okay, and so let's look at the causal structure. Now, in the Bayesian network, the root nodes represent the original causes. There's nothing dependent on it. In this case, pollution and smoking status are the original causes. The leaf nodes represent the final effects along a chain of influences. And so smoking can cause cancer. It influences cancer status. And that cancer status influences the final effect, which is the X-ray showing up. Likewise, smoking influences cancer. Also, dyspnea influences dyspnea, which is shortness of breath. Pollution, the same, influences cancer, shows up on X-ray. Pollution influences cancer, shows up as shortness of breath, dysnopia. Okay, and so pollution and smoker are root causes. X-ray and dyspnea are the effect for this Bayesian network. And so here we're depicting all of the influences among these different variable measurements. And so we specify these dependencies, causal dependencies, based on the knowledge engineer. And there are algorithms that will build it for you, and we'll talk about that in another module. But you specify your conditional probability distributions. Once you have this graph, these dependencies, you specify conditional probability distributions for each one of the nodes. And these are depicted in table format, as we have here. And these tables are called conditional probability tables, or CPTs, therefore. And what these CPTs consider is all of the possible values of the parent. So each CPT for a given node, like say cancer, because it's two parent nodes, its influences are pollution and smoker, it's going to be indexed by all of the instantiations for the values of the two parent pollution and smoker node, those values. And so we have 4 entries here. Now there's another table with 4 entries corresponding to the probability that cancer is equal to false. And you can just compute that by taking 1 minus each one of these entries for probability that cancer is equal to true. Okay. And so for the cancer node, its parents are smoker and pollution. It takes on joint values, high and true, high and false, low and true, low and false. And so the first position is for pollution. The second position is for smoking status, true or false. And so for this, we have the following values. For the first instantiation, we got 0.05, then 0.02, then 0.03, then 0.001. And then for the probability cancer equals false, it's just 1 minus that. So that's 0.95, 98%, 97%, and 99.9%. Okay, or 0.999 probability. All right, and so for the root nodes, you notice we have 1 row representing the prior probabilities. So we have for pollution low, it's 0.9, and therefore for pollution is high, we're going to have 0.1, law of total probability. For pollution, smoker equals true, we're going to have another entry, pollution probability probability of smoking equals false is going to be 0.7. Okay, and so the conditional probability table depends on the number of parents. The more parents you have, the more entries you're going to have. If you have 2 parents here, you have 4 entries. And so given n many parents, you're going to have 2 to the n entries, assuming that it's binary. You change it from 2 to whatever that base is, if it's 3 values, what have you. So assuming binary, you're going to have 2 to the n plus 1 entries. What does that mean? Okay, well, you have 2 to the n for the true alternative, if it's true and false, and then another for the false alternative, so that's the extra 2. So you have a total of 2 to the n plus 1 many entries in your conditional probability table. And so that just means if you have a lot of influences for a node, so if you have some node x, and it's influenced by some node y1, y2, ... yn, it behooves you to make Bayesian network classification more tractable. You want to make these CPTs as small as possible, so you're trying to limit the number of parents to be relatively small. Okay, so let's take a look at how you would use these to reason over various things. Now, Bayesian networks, when they originally really came into being in the 80s, there was a really big win with medical diagnosis, where you input a lot of information from medical records. And so these Bayesian network reasoning requires an assumption of the so-called Markov property. There are no direct dependencies modeled that aren't already shown. So the graph captures known dependencies in practice, but not all the dependencies. As long as you're not modeling a dependency that doesn't exist, that's fine. You don't have to model all of them. But those that are modeled, they have to exist in the data. And so in this case, smoking does not directly influence dyspnea, except by way of causing cancer. There's no direct dependency between smoking and dyspnea. And so there's no backdoor relationships allowed in Bayesian networks. And so Bayesian networks that satisfy the so-called Markov property, meaning that only existing dependencies are modeled, they're called I maps, I for independence, independence maps. It models completely all those conditional independencies associated with your variables. And so what we strive for in general is fewer dependencies. These give us smaller models because fewer dependencies means smaller conditional probability table entries. And so in essence, we'll prefer to treat things as independent that actually are dependent, because it means that we can have smaller models which are more tractable. Is that absolutely faithfully correct? No. We're losing information, but there's always a trade-off between tractability and specificity. Okay. And so a dependence map is one that captures true dependencies, but not necessarily all the dependencies. And you can have a perfect map, i.e. an information map, which is nothing more than just the dependence map where all of the true dependencies are modeled. So this capturing of dependencies that matter, you're in effect picking a factorization of the joint probability distribution. We said when we talked about the chain rule, we kind of peel off these query variables and condition variables, and each way of organizing them, applying the product rule again and again and again, represents a factorization. So in essence, what we're doing when we draw the dependency graph, we're saying, okay, I'm going to choose certain factors that I can multiply together, and then everything else that I don't choose when I represent my dependencies for my graph fragments for the Bayesian network, everything I don't choose, I'm just going to consider as being independent. And so you're in effect, when you create this dependence graph graphically describing the Bayesian networks, you're picking a factorization of this joint distribution. And so how do you do reasoning? Well, you observe the value of a variable, and you condition on this information via a flow of information through the network. And this might mean updating the beliefs or the probabilities. You could use them to perform inference, to sample, and then compute statistics over the data, or you can propagate probabilities. And now, given values or evidence of some of the nodes in the BayesNet for observations, you're going to propagate the result of those observations through the rest of the network in order to make reasoned judgments based on those probabilities resulting. Okay, and so one type of reasoning is called diagnostic. And in this diagram, we call the evidence the thing that you're going to condition on. And so here we have dysnopia as our evidence. It's your root node. You go to the root node, the end effect, and you condition on that, and you set it. And once you set it, then you go up in the opposite direction towards the root, trying to find the root cause. And so with diagnostic reasoning, you observe a symptom, which is an effect, an end effect, like dysnopia. And then once you observe it, you condition on it, this evidence, and you update the belief about what you think, how cancer is going to change in its probabilities, and also if the patient is a smoker. And so you're traversing up the tree in the reverse order of the directed edges, opposite the direction of the arcs. That's called diagnostic reasoning. You're taking an end effect that you observe, dysnopia, shortness of breath, you're setting that probability, and then you're evaluating the consequence on all the other probabilities or probability tables going against the direction of the arcs. The other type of reasoning is called predictive reasoning. You have new information, you set that probability for that new information, and then you go down the tree, the BayesNet, in the order of the arcs. And so let's say you're interviewing a patient as a physician, and someone says, yeah, I'm a smoker. And so before any tests are performed, you evaluate, given this, yes, I'm a smoker, what the consequence is for the subsequent probabilities going in the direction down the arcs. And so that way you can look at the probability that because you know this patient is a smoker, what's the probability that the person might have dysnopia or have a positive X-ray result. So in the case of predictive reasoning, you're taking the root cause as evidence, and you're reasoning down the tree, evaluating the consequence of setting that evidence to be true in the probability or probability table for that node, and then evaluating the consequence going down in the direction of the arcs. So then there's something called intercausal reasoning. Intercausal reasoning is here, down in the lower left-hand corner, and intercausal deals with the relationship between two possible causes, and it relates to what's called a V structure. So here we have a V structure. We have pollution, we have this influence on cancer, and then we have this other influence on cancer from smoking status, and it forms a V, hence the name V structure. And so what explaining away does is that you have two possible causes, or V structure. So here we have cancer, and the two causes are either pollution or smoking status. So you have two possible causes, and you want to know which effect has a greater influence. And so here we have our evidence is going to be cancer. Someone has cancer. You're going to condition on that evidence, whether the cancer status is positive or negative, true or false. And then you want to see, okay, what's the impact of smoking status and the impact of smoking status on the pollution. And so you have two possible causes. Smoking and pollution have a common effect, namely cancer. And smoking and pollution are independent of one another, given some evidence on cancer, and you don't know which one of them can lower the probability of pollution exposure. Is it cancer or is it smoking? And so therefore, you're going to condition on evidence here. There's the cancer, the common effect. They're conditionally independent. The pollution and the smoking status are conditionally independent. And then you try what happens if my smoking status is true or false, and look at the impact on pollution. And so essentially what you're doing, pollution and smoking are independent, but knowing one of them can lower the probability of pollution exposure more than the other. And so which one? Is it the cancer or is it the smoking status? And so you reasoning through the impact on probabilities associated with a V structure, and that's called intercausal reasoning. Okay, so any node in this BayesNet can be an evidence node, and based on how you update probabilities as a consequence of setting evidence, you can use this Bayesian network probabilistically to do diagnosis, to do reasoning, and to look at the interaction between effects. And so any node can be an evidence node. You condition on, or you set to be true or false or with some value. And then any node can be a query node, asking some question about what is the most likely probability resulting from the observation of that evidence. And so that's all I had. Bayesian networks are immensely powerful. And at this juncture, we assume that the Bayesian networks are designed, but we will also, in a future module, talk about methods for automatically constructing these Bayesian networks along with the associated issues. So with that, that's all I had for today. We'll end here. And as usual, please stay healthy, stay safe, and I'll see you all on Thursday.